Hi, this is Dr. Xu teaching mine ventilation for mining engineering college students. In today's video, we will talk about heat source from machinery. The operation of all mechanized equipment results in one or both of two effects. Work is done against gravity and heat is produced. A conveyor transporting material up and incline. A shaft hoist and a pump are examples of equipment that work primarily against gravity. Vehicles operating in level airways, rock breaking machinery, transformers, lights, and fans are all devices that convert an input power via a useful effect into heat. Increasing utilization and power of mechanization in mines resulted in such equipment drawing geothermal effects and autocompression as a major source of heat. For electrical equipment, the power taken by the motor is split to useful energy here and direct heat loss from machine body here. For example, if the efficiency of the motor is 90%, the useful energy is POW by 90%. And the direct heat losses from machine body is POW by 1 minus 90%. That equals to POW by 10%. So this is heat losses from machine body. The useful energy is split to work done against gravity here and heat dissipated along working length of machine here. This part, heat dissipated along working length of machine, equals to useful energy minus the work done against gravity. For horizontal conveyors or pump, work done against gravity is 0. Thus, all consumed power manifests as heat for horizontal conveyors or pump. If it's not horizontal, the work done can be calculated if we know the change in elevation. The power taken by electrical equipment can be calculated if we know the voltage and amps of the electrical equipment. For AC power, we use this equation, and for DC power, we use this equation. The work done against gravity can also be calculated by mass divided by time, by gravity, by the change in elevation, and divided by 1000 to convert it to kilowatts. For pumps, the mass divided by time is pump flow rate, liter per second or kilogram per second. For conveyors, mass divided by time is the shift average mass divided by shift time equals to kilogram per second. Let's have a look at this example. A 2,000 meter long conveyor transports 500 tons per hour through a vertical lift of 200 meters. If the conveyor motor consumes 1000 kilowatt at a combined motor transmission efficiency of 90%, calculate the heat emitted. We will go back to this diagram. The total power here is 1000 kilowatts. It's divided by 2 and the motor efficiency is 90%. So the direct heat losses from machine body equals to 1000 by 1 minus 90% equals to 100 kilowatts. And here the useful energy U equals to 1000 by 90% equals to 900 kilowatts. Work done can be calculated using the mass divided by time, that is 500 ton multiplied by 1000 to convert it to kilogram, divided by, this is per hour. In 1 hour there is 60 minutes, and in 1 minute there is 60 seconds. So this is kilogram per second. Multiplied by gravity, 9.81, multiplied by the change in elevation is 200, divided by 1000 to convert it to kilowatt, equals to 272.5 kilowatt. Therefore, heat dissipated along working length of machine equals to 900 from here minus 272.5 equals to 627.5 kilowatt. Let's look at another example. A conveyor draws 750 kilowatt when offloaded and 1000 kilowatt when loaded over a change of elevation of 180 meter. The belt operates for 6 hours for an 8-hour shift. So in that 8 hours, only 6 hours is on. Therefore, 1 hour is offloaded. 2 hours is off. And the drive head motor efficiency is 90%. The total shift production is 5,000 tons. So the shift production is over a time of 8 hours. Although the belt only operates for 6 hours, we will need to divide that by 8 hours because it asks for the average heat dissipated through the rollers. Firstly, we will calculate the work done. That equals mass divided by time. That equals to 5,000. That's tons converted to kilogram divided by 8 hours by 60 by 60. So this is a minute, this is second. So the whole thing is kilogram per second. By 9.81, that's gravity, by change in elevation divided by 1000 to convert it to kilowatt equals to 306.6 kilowatt. The average power consumed equals to, that is 1 hour offloaded plus 5 hours loaded, that's 1000 kilowatt, divided by 8 hours. So over the 8 hours, I want to calculate the average, equals to 718.8 kilowatt. So the average heat source equals to total power minus work done. Total power is 718.8 minus work done is 306.6. That equals to 412.2 kilowatt. Heat dissipated at driver motor equals to the power consumed, 718.8 by 1 minus efficiency, equals to 71.9 kilowatt. Therefore, the rest of them are dissipated through rollers due to the friction between the conveyor belt and these little rollers. So that equals to 412.2 minus 71.9 equals to 340.3 kilowatts. For diesel machinery, we can calculate the heat from utilization. So in this equation, RP is the rated power of diesel equipment. PTAV is the percent time available. PTUT is percent utilization. That's the load over the maximum load. For example, a truck can be 80% loaded. And eta is the efficiency. For diesel equipment, the efficiency is normally 33%. We can also calculate the diesel heat from fuel consumption. Sometimes this is easier because the fuel consumption in a mine is easier to be monitored. In this equation, the heat can be calculated from the quantity of fuel used. The fuel density is known here, and the calorific value of diesel fuel, typical value is given here, and the total operating time during which, and we need to know the total operating time. Let's take one example here. A diesel unit has a rated power of 110 kilowatt and is operating at an average continuous load of 30%. So loaded 30%. If the unit is used for 5 hours in an 8-hour shift, calculate the shift average heat generated by the unit. So efficiency is 33%. By use this diesel heat from utilization, we know that RP equals 110 kilowatt and eta equals to 33%. PT average equals to 5 divided by 8, and PT utilization equal to 30%. If we plug in these numbers, we can calculate Q equals to 62.5 kilowatt. Here is another example. A diesel unit has a rated power of 110 kilowatt and is operating at an average continuous load of 30%, the same with the previous question. If the unit is used for 5 hours in an 8-hour shift, how much diesel fuel would it have consumed? Diesel unit efficiency is given, diesel calorific value is given, and the diesel density is given. From this equation, we can derive that the fuel consumed equals to this. On the right hand side, we need to find out the heat generated from this diesel equipment. From the previous question, we know that this Q equals to 62.5 kilowatt. Therefore, QF equals to 1000 by 5 hours, convert to minute, convert to second, by heat generated from this diesel equipment, 62.5. DF is 845 by CF is 45.6 by 10 to the 3. This is a kilojoule per kilogram. Need to convert it to joules per kilogram, equals to 0.0292 cubic meter, equals to 29 liters. Alright, in this video we have talked about heat from machineries, especially from electrical machineries and diesel machineries. Thank you very much for watching. This is Dr. Xu. I will see you in the next video.